Okay.
All right, thank you everyone for coming. I'd like to start by acknowledging the traditional custodianship of the land on which UOW is situated. We pay our respects to the Aboriginal elders past and present, who are the knowledge holders and teachers. We acknowledge their continued spiritual and cultural connection to country. As you share knowledge, teaching, learning, and research within this university, we also pay respect to the knowledge embedded forever within Aboriginal custodianship of country. Our speaker today is Dr. Nicolas Flament. He has won several rewards for his work on dynamic Earth models, including the Anton Hales medal last year, and more recently, the David Syme Award. So please welcome him up.
Thanks, Ron. Thank you guys for coming. Let me just do a couple of things here. I'm gonna hide the meeting controls and grab a pointer. Okay. This is work that started in 2018 during a holiday with a deadline for a conference, together with, at the time, Simon Williams and Andrew Meredith. Andrew had developed a tectonic reconstruction, the first one with fully closing plates that goes back to 1 billion years ago, and that opened up new opportunities to look at things that people couldn't have done for mantle convection. And Simon helped me a lot with the analysis. Then Omer Bodo joined us here at UW in 2019, and he's done everything that's in terms of 3D visualization and a fair bit of the data crunching here. The title is Setting the Law Mantle Free, and it will become clear why there was a bit of a problem in geodynamics, and these new reconstructions gave us the opportunity to contribute to that discussion, to that debate. And this is a industry-funded project through a linkage project with De Beers as the partner, industry partner, and obviously the Australian Research Council chipping in a fair chunk of the cash. All right, there's two blobs in the Earth, and we've known about these two blobs for perhaps about 40 years, perhaps a bit more. And we know there's blobs, we don't know much more, and as more data comes up, these blobs, they tend to become more and more complex. There's one blob under Africa, here, and one blob under the Pacific. The blobs extend from the core mantle boundary, and if you've never heard of that, that's about 3,000 kilometers down. And to give you an idea, that's about the width of Australia down into the Earth. Okay, and then they extend up. We don't know exactly how far up they go, perhaps 500 kilometers up. In this picture, in this image, it's clear they go further up than that. Okay, perhaps 2,000 kilometers up. So it depends how you define the blob. There's many questions about these blobs. What are they made of? When and how were they formed? Okay. And then another question, which is the one I seek to address today, is whether they have remained in the same position over time or whether they have moved over time. And here they're imaged through tomography, and they are represented as a seismic velocity anomaly. So essentially with that, all we know is that S waves, and also now we think P waves, travel more slowly through the blobs. And that's an indication that the blobs are hotter than mantle around them at the same depth. And then there's a bit of a debate about, is there also a compositional signal in there? So are the blobs just hotter, or are they also compositionally distinct? And if they are, they would be denser than what's around them. So let's look at them in 2D. And I'm doing this because comparing 3D against 3D is tricky. It's the same model, S40RTS. And now we can see very clearly under Africa here, the African blob, and under the Pacific Ocean, the Pacific blob. And everything that's around is not slow. And essentially, if you're a geologist, you might recognize the ring of fire there. So at the surface, we have these volcanoes linked to subduction zones. And in the very deep Earth, it seems we have a ring of non-slow velocity anomalies there. So there seems to be a link to subduction zones. Another link was established about, well, in 2010. The first paper on this was in 2008, I believe, and that's the crux of the problem. And the insight, there's a couple of insights here that are very important. The insight is that reconstructing large igneous provinces, so these are igneous provinces the size, for example, think the Deccan traps that wiped out the dinosaurs, that kind of geological object. Okay, so there's significant events. There's only about 25 of them, and which ones are selected as a large igneous province of deep origin depends on the authors. It's unclear, and that's on a case-by-case basis, it's debated. Okay, so the 25 are these green dots here, and you see there's more around Africa than around the Pacific blob. And so these were shown when reconstructed at the time of eruption and shown at the present day to cluster around the blobs. There's not very many of them, and another idea was to use kimberlites, and kimberlites were also shown, and kimberlites are exclusively in the African hemisphere because they're on continents. There's very few continents that have traveled over the Pacific hemisphere, but the kimberlites also seem to coincide with the blobs. Okay, so the authors of that paper went a bit further. They said these lips and kimberlites, they coincide not only with the blobs, but with the edges of the blobs. There's a set of kimberlites in North America that doesn't work too well, but that's a detail. And then having a fixed point in the earth is kind of a holy grail, because when we go back in time, before 200 million years for tectonic reconstructions, there's no ocean floor. And that means we left with paleomagnetic data, essentially. And paleomagnetic data are good to constrain the paleolatitude of continental blocks, but not the longitude. And so this idea here was that, well, if the blobs are fixed and the volcanoes or volcanic products come from the deep earth, then that means that any block carrying a lip or kimberlite could be pinned to the edge of a blob. Okay, so that in tectonics, that's kind of a holy grail, and that's why there was a desire to have a reference, and that reference was having these two blobs assumed fixed. Why assumed fixed? Because that correlation works so well for the last 320 million years that it's been then extended to say, well, if it works for 320 million years, surely it has to work for, and then people have said 500 million years, and some others have said, oh, forever. Okay. Now, this is a bit difficult to reconcile with the current understanding of geodynamics. The kind of models I'm going to present today, I didn't invent them. People have been using them for 20, 30 years. And in these models, what we see is that slabs, so this is sinking oceanic lithosphere, sinks over tens of millions of years into the Earth mantle and pushes material away as it does so. And that is the material that's hotter. So in the geodynamic models, what we see is that the blobs are swept away or moved along by the slabs. Okay. And again, here at the top, you have the two blobs, and in blue, what would be the slabs. And you see the hotspots. Again, here, this is a different catalog of hotspots. And that's where it gets a bit messier or trickier. At the top, what this figure shows is the location of subduction zones from a reconstruction. So there's a fair bit of uncertainty here. Some of these subduction zones probably didn't even exist. Okay, possibly didn't even exist. But that's the best that's the best set of reconstructions we have. In the background, you have these two lines, and these show where tomographic models agree. It's out of 5 tomographic models agree. And the dashed line is at least 1, and the solid line is 5 tomographic models for the location of the blobs. What you can see is that for the last 200 million years at the top, subduction zones are nicely behaved away from the blobs. And so all is in order. It seems that that concept of subduction zones and sinking slabs shaping the blobs works. And that would explain the volcanic record for the last 200 million years. The thing is that if we go further back in time, a couple of things to notice. These subduction zones seem to be a lot more mobile, and also they cross over the present day location of the blobs. So what we expect if sinking slabs sweep the blobs away is that the blobs should move. However, colleagues who made the correlation said, well, why do you need moving blobs when fixed blobs do explain the data? Okay. So what did I do? And that's a game I've been playing for far too long, and it's embarrassing to talk about it, but that's my game. I used tectonic reconstructions developed by my collaborators in Sydney. And so these, we now have a set extending back to 1 billion years. And we're working on 1.8 billion years, which becomes, obviously, as you go further and further back in time, it becomes more and more uncertain. It might still be useful for some things, though. So we couple these tectonic reconstructions with a modified version of a piece of scientific software designed to solve for flow within the Earth, for mantle flow. So these are the Navier-Stokes equations, essentially, without any of the Coriolis forces, any of the eddy effects, because there's no inertia in the mantle. So it's a cheaper way. Well, the problem that has to be solved is not as complex as for ocean dynamics, for example. So these models, the reason we modified them, essentially, is these models, they're too crude to capture the dynamics of subduction zones. So we cheat, and we impose the subduction history at the top. So we have a hybrid solution where we impose subduction at the top, and in the bottom, we have the dynamics of the mantle. For this, I use supercomputer GADI, which is, at the time it came online, was one of the best in the world, and now it's 100 or so. So we need more money to do supercomputing research in Australia. And hopefully this comes along at some point in the near future. And so here's what we get in the end. We get this kind of picture, and I'll show you more of these, with the sinking slabs here highlighted in blue, and they are colored by depth. So the darker blues are deeper in the mantle. I won't agonize over the details of the mantle convection models. I'm happy to entertain. I'll give you just the keys you need for your understanding here. The initial condition is based on the tectonic reconstruction at 1 billion years ago. You can see on the left as a 2D annulus that goes through the equator, I think, and on the right as a 3D representation. The slabs are inserted to 1,000 kilometers depth in the initial condition. So you can see some here. The temperature increases down into the mantle, and at the base, there's a homogeneous layer. There's two things about that layer, where it's hotter as expected, and also it has, here I've assumed it's got some, sometimes I put some, it's chemically distinct, okay? And I vary this. So I have one case where it's purely thermal, and then I vary its density over a series of cases. And another thing I need to mention for the purpose of this talk is that the continents also have some chemical traces. So numerically, what we use is traces that represent a composition field. Okay, this is important. This is the subduction history that we impose in the models. And we start from 1 billion years ago down here, and then we go to 700 to 500 million years ago, then to 500 to 250, and the last 250 million years. They are shown, subduction zones are shown in around about 100 million year interval here, I think. And what you can see clearly, again, as on the earlier picture, is that back in time, some subduction zones overlapped with the present day position of the blobs. And again, you have them as the lines are inverted, but you have these two lines again for your eye, which is where 5 tomographic models or 1 agree where the blobs currently are. Okay, so intuitively here, if you take the point that the subduction history shaped the blobs are going to change over time. That's only part of the job done, and we could do a bit more. And so now I'm going to show you not the full result, actually, the last 200 million years. This is going to be nice and smooth. I'm going to show it to you twice. It's in 1 million year increments. There's a lot going on here, so let me describe before I play. In white at the surface, you've got, if I find my laser pointer, okay, it's a bit laggy. In white at the surface, you've got the coastlines. If you are a geologist, you might recognize India down here, I think. In green, you have plate boundaries. And this would be Spain just here, actually. Or the Iberian Peninsula, I should say. In green, you have the plate boundaries that divide plates. And inside the Earth, in blue, are the slabs that are cold, followed by depth. Darker is deeper. And the blobs are in the red to orange, colored by depth, and darker is shallower. So let's play this. I think it will go twice. And it should go in full screen too. And two things to notice are things move, new subduction zones appear, the blobs move. Here we're looking on the African hemisphere, and you're going to see Africa, the opening of the South Atlantic Ocean, and now you can see Africa clearly moving north. And as it plays again, I'd like you to focus on what happens on the African blob. And you can see here at the end, we have a nice solid blob, but earlier in the history of the model, for this history of convection, there actually are remnant slabs. And so image with tomography 200 million years ago, probably the image wouldn't have been one solid blob. Okay, so that's the key to this story, essentially, that there's rust or slabs of cold material within the blob. And over time, they warm up as the blob assembles, pushed by subduction from the northeast and the southwest, in this case, mostly. Cool. So I can look at this in 2D as well. And when I do, I'm going to do this to show the similarities and differences with the tomographic models. Well, one in particular. So now this is the same result as I showed on the second slide, I think. But instead of having a tomographic model, we have the predicted mantle temperature for the present day. And what you see is that we have two main blobs. One under Africa, it's got a bit of a funny kidney shape and it's a bit too elongated. And one under the Pacific Ocean, that's a bit larger than the one in tomography. Same depth as in the tomography, though. And so what I want to do next is compare these two. And when I go from one to the other, it's obvious I'm using two different color scales because they're two different physical quantities. One is temperature, and the other one is seismic velocity. It's possible to play a game to convert seismic temperature to seismic velocity, but you need to assume a number of things. So instead of doing this, I've played another game, which is cluster analysis. So in this game, what I do, I take, and here I'm considering the mantle between 1,000 and 2,800 kilometers depth. So the bottom third, 2/3 of the mantle. And I ask an algorithm to sort points thrown at the surface of the Earth into two categories, depending on the variation of quantity with depth. Okay. The first quantity here is for the tomographic model, and it is the seismic velocity anomaly. Essentially, what the clustering algorithm does, it minimizes two populations, or the distance to two populations. And what we find is that there's a slow population and a fast population. And here's the graphical depiction, geographical, I should say. And so gray is the slow and white is the fast. Okay, so that's one way to get to a new representation of the blobs where I've condensed 1,000 kilometers onto one map. And then I worked out that the blobs represent 35% of the area, 34, which is similar to the continents at Earth's surface, which is interesting. And now here's the same exercise, but this time it's done for the mantle flow model. And what I've done, well, in this case, what it gives is a hot and a slow cluster. And that's how they map. The hot one is in gray and the slow is in blue. Interestingly, for this particular model, we get the same fractional area, which is 34%. However, when we look at the details of how the two compare, I can work out the score. There's different ways this can be done. I'm doing it here in a quite naive way, actually. And I'm using what I call the accuracy. And so orange is good news on this map. but gray is also good news, okay? And the accuracy score I'm showing takes the gray into account. Blue and green are bad news. Green is a false positive, which means the model predicts the blob, but the tomography doesn't see a blob. And blue is a false negative, which means the tomography tells us there should be a blob, but the model doesn't see the blob. The score I get here is 72.72, which you can think of as 72%. But I need to reiterate that it's driven up by this large area of gray here. Okay. There's another score that doesn't take the area of gray into account. That would be lower. It would have the same trend across a series of models. Okay, so this allows me to say, hey, my model is okay for the present day. But the next step was to try and define a way to assess how good it is through time. And so to do that, I was inspired by the work that linked the blobs to the volcanic products. And so what I did, I used two databases of volcanic products. I'll start with the easy one, which is the Tapper et al. And it's thrown, and I should have done this the other way around, but such is life. The dots are kimberlites, okay? There's many of them, that's why it's good, statistically, it's good to have many points. So kimberlites, we have 763 for the last 320 million years. And again, they are mostly in the African hemisphere. And the second one, which are shown as diamonds, and I should have used that for kimberlites because kimberlites can be diamond bearing, but I use that for large igneous provinces. These are from Johansson and others, or Johansson, I'm not sure how his name is pronounced. One thing to say about this, it contains both the plumed heads, which is the giant outpour of magma, but also the plumed tails. So if you think about the Hawaiian polar band, for example, that is in this database, which others would exclude. And here's what the data look like in terms of a time series as a histogram. So you can see that large igneous provinces in red. There's never more in 20 million year increments here. So what I've done here, because my results for my model will be in 20 million years, for each data point, I've resampled it onto a 20 million year window, sliding window, if you want. And we can see we never have more than about maybe 30 or 40 large igneous provinces. However, at times there are up to 160 kimberlites or so. And what I've done, I've actually combined the two. And so in the results I'll show you next, I'll be combining the two databases, kimberlites and large igneous provinces. And that's where the fun kind of begins. Although half of you are almost asleep already, so thanks for bearing with me. And do ask questions if you need to, or if you want to. The next thing I did was to measure the distance of each of these volcanic products in the database to either the predicted blobs from the mantle flow models or the blobs from the tomographic models. So I'll show you an animation. On the right-hand side, things will not move. This is the world in which the blobs are fixed. And on the left-hand side, things will move. Okay, and again, we have the diamonds are the large igneous provinces, and the dots are the kimberlites. And then just for the next slide, what you need to know is that when I compute distances, there'll be 0 right on the edge of the blobs, there'll be positive inside the blobs, and there'll be negative outside the blobs. I think this will play twice again. We start at the present day, go back in time. And what I want you to take from this is that overall, the volcanoes are close to the fixed blobs, and that had been established before. But they're also close to the moving blobs, and that hadn't been established before. Okay, and that was the crucial point that the team in Norway used to argue that, well, the data agrees with the fixed blobs, so why do you need moving blobs? So essentially all I did was to show, well, the data also agree with the moving blobs. All right, so we've seen this a couple of times now, and we'll actually see it again. And so the next thing I did was a bit of stats. So that took me some time, and it was a bit of a steep learning curve for me. These are called empirical distribution functions. So it's like looking at it as a histogram, but you've unfolded it and you're looking at the distribution unfolded, or in a cumulative sense, if you want. Again, on the left-hand side, this is for the mantle flow model. On the right-hand side for the tomographic model. What I report here is theta, which is the reading at 0.5, which is the median. It's -1 for this distribution, and it's -4.2 for that one here. So that is negative tells us that in a median sense, the volcanoes are slightly outside the blobs. Okay. And so the two measurements are similar, but then the next thing was to do statistics. And so what I did was I randomly sampled points that have the same temporal distribution as the databases. And then I measured the distances from these points to the nearest blob again, okay? And I'm going to show you one iteration, and I'll show it to you twice, but I did 1,000 iterations for each case. And this is going to look like chicken pox, and at times you just go like, what's going on? I can see many, many red squares, but I can't see very many of the other points. And the reason for that is that the kibolites, they come in clusters. And so they're all on top of each other. Whereas my random points, I allow them to be anywhere. And so that's why at times when there's many kibolites, when there are many kibolites, you end up with random points all over the place. And so the test after this was fairly simple. It was to compare the distribution of the sample to each of the 1,000 iterations. And that's what this looks like. So you have gray lines here in the back, and there's 1,000 of them. And for each of them, I did two things. The first thing I checked is that the blue line gave a mean in an absolute sense. So I took the because it's a part of the distribution is negative. I folded the distribution over to the absolute values and made sure that the blue predicted a mean that was on average that was lower than the gray. That was the first part of this test. And the second part of the test, it's called the Kolmogorov-Smirnov test. And in a set, it's a test that assesses that this blue distribution is significantly different from the gray distribution. And I did that for every single one of the 1,000. And I reported a fraction. So the two criteria have to be met. And if they are both met, we get add 1 out of 1,000. And you can see on the left-hand side, they all passed. And on the right-hand side, 97% passed. Okay. So this confirms that in a statistical sense, and that's based on previous work, or similar to previous work, but done in a time-dependent way for the first time, that the blobs are related, or rather the volcanoes are related to the blobs. It's true for the fixed blobs, but it's now also true for the moving blobs. And so that's all I did, is to show that in a sense, it's not required to have fixed blobs to explain the history of volcanoes at Earth's surface. This is the part that gets a bit gory potentially, but I'll keep it light. I now have 4 metrics. This is the area. This is the first one I presented, that was 34% in both cases. This is my accuracy at present day, and that's the one where I presented it to you was 72%. This is the distance, where we had -1 and -4 in the example I presented. And now this is the stats, the results for the statistical test. At the top, I have a series of tomographic models. And at the bottom, I have 2 series of mantle flow models. Okay. And I take the tomographic models in each time as the target. So that's why I have these gray bands. And then I search in my models. I have many buttons in my models. Here, I'm just tuning 2 buttons. One button is the viscosity of that basal layer. So if it's less viscous, it can be deformed in a different way than if it's more viscous than what's around it. So I kept it ambient, or made it 10 times less viscous than around, or 10 times more. And it turned out that 10 times more was a bit more favorable in terms of the present day accuracy. and maybe the median as well. So I went with this one, and then I did another series, and that's the important one. I varied the density of the basal layer. That's been debated a fair bit, from 0% to 2% with increments of around about 0.5%. What I found in terms of the accuracy, there seems to be a sweet spot at 1%. And in terms of the distance, there seems to be a sweet spot, and the area as well, there's a sweet spot at 1.3%. Key thing to note here is that there's no model that is in the gray band for all criteria or all metrics from the tomography. And my preferred case was C7 here, which is very close for accuracy and good for area. Obviously, the target area is a big one. There's just one more thing I want to alert you to, and it's a bit of it's a limitation, and it's not fully understood what's going on. The results I presented to you just now, the net rotation of the lithosphere has been taken out. What does that mean? The lithosphere as a whole, with respect to the mantle, moves over time. We know it's a known unknown. We know there's some, but we don't know how much. Okay. For mantle flow models, it's good to remove it at the surface because this arises from the convection. I'll just say that. And so this is why these are the results I showed to you. But this is the figure I showed a few slides ago. When I use this reconstruction, it shifts where the volcanic products are. And in a sense, it changes the results. Okay, so this is a paleomagnetic reference frame for anyone who's interested, which is the one that ships with this reconstruction, and then we modified it. And just why did we modify it, and why is it important? So I'm back to this series of results, and what I want to point out to you, and maybe I should do it here first. Here, the volcanoes are inside the blob mostly, and here they go outside the blob. And you can see this here. Values here are, in the median sense, positive, which confirms inside the blob. And here they go negative for this other reconstruction, which is outside the blob. Okay. At the bottom here, what I have is two mantle flow models. One is based on the original tectonic reconstruction, and the other one with the net rotation removed. They're overall similar. And there's one big difference, it's the accuracy at present day. And I just want to highlight that for you. I'm going back to this slide that you saw a few slides ago. And I'm going to show you the other one. It's completely screwed up. So if I use that other reference frame, I get my blobs to be, there's one in the Arctic, apparently. The one in the Pacific is shifted to the west, and so is the one under Africa. And that's been known for a fair bit of time, that in these convection models, with net rotation, there's a shift that occurs of the blobs. And that's why I removed it in the first place. But that's a big effect. There's two more parts of my story I'd like to tell you, and I'll try to be entertaining. It's been thought for a while that there's a link between upstairs and downstairs, if you want, the supercontinents and the blobs. And this is a very cool paper from 2007, where it was shown that with no continents, Earth would be the mantle would be probably in degree 1, which means there would be a giant upwelling on one side and a giant downwelling on the other side. And what that research did, these are not time-dependent models, but it's still a very nice concept, is to show that if a ring of fire or if a subduction girdle exists, then there's a degree 2 Earth with one major blob away from the supercontinent that would be here at the surface, and one smaller blob under, which is a degree 2 Earth now. That's one aspect. And the second aspect is, because until this work, reconstruction was limited to 400 million years, models couldn't extend further back in time. And these are models similar to the one I just showed you. And these models predicted that the African blob had existed from at least 200 million years ago. However, the movie I showed you shows differently. And why is that? This is back to the tectonic reconstruction that we used, and I've highlighted a few things. So WGB is West Gondwana block at 740 million years ago. What you can see here, there's a lot of subduction zones there, and maybe some of these are real, maybe some of these aren't. They're in the model. And then there's two other subduction zones that play an important role in my model, which is the Paleothetis northern margin and the Gondwana western margin at 400 million years ago. So let's take a look at how this could have affected the deep Earth, or in the models, what the history of convection is in the model. So again, we have the plate boundaries in green at the surface and the continents in gray. And what we have here, we've tracked the path of subduction zones as they sink into the Earth's mantle. And this is that network from 740 million years ago. And over 250 million years ago, it had created a giant cold slab that was very deep in the Earth's mantle. And it was so large that the model predicts that that would still have existed at 80 million years ago. Okay. And then there's a push from the northern Tethys margin, Paleothetis margin, and from the Gondwana margin that brings that blob together. So for this particular model, the African blob wasn't one super blob 80 million years ago. Let me show you this as a movie. This is the network that dumps cold material deep in the mantle. If you track this, if you follow my cursor, that slab takes then a very long time to be warmed up. Okay. And it's the last slab that is, that's a hole in the African blob. And if you take a step back from that and you look generally, the African blob has moved about. It's always smaller as expected than the Pacific blob in these models. These models don't have much subduction in the Pacific hemisphere, which might be a shortcoming of them. Cool. I'm going to show you this one once more because it's much smoother. And this is the West Gondwana slabs. This is it. And that's the one that is a hole. Well, there's a couple more. That's the main gap in the African blob until that 60 million years ago, I think, in this case. And then we have the African blob that's a coherent blob. Now, it's unclear from tomography whether it really is a coherent blob because there's limits as to what can be resolved from the tomographic models. And finally, for any geochemists in the room, there is a geochemical implication to this work. About 38 years ago, this paper here mapped, so these are lead isotope anomalies for 207 or 208. And essentially, my understanding of this is that 208 anomalies were mapped as being positive in the southern hemisphere or along this line here and negative elsewhere. And the idea was that there was a hemispheric distribution of lead anomalies in the mantle in a north-south sense. Recently, or more recently, work by the Curtin group revisited that concept in the context of the blobs. And their proposal is that there is a distribution of the lead isotope anomalies, but they're linked to the blobs. Again, they selected only, this depends on which plumes are selected. So there's a bit of geochemical dark magic taking place behind the scenes here. Here's their results for the African blob and the Pacific blob. They're plotting 208 as a function of 206 lead anomalies. And what you see clearly shown this way is that there's a deviation on the African side that you do not see as much on the Pacific side. And the interpretation from the authors was that, well, there's continental crust that has been subducted down to the deep mantle and is in the source of these plumes on the African side, but not on the Pacific side. That kind of makes sense to a point. It makes sense because in the last 200 million years, at least, the African hemisphere has seen a lot more continents than the Pacific hemisphere. Now, the counterpoint is that over the history of the Earth, we don't know. So it's possible that the Pacific blob would have been enriched, but earlier in Earth history. What we did in our models, as I mentioned, we have continents, and this is an artifact of the models. These continents get entrained to depth. It used to annoy me, but it became a benefit because we can look at this snow of continents. And obviously, because we have more continents on the African side, you can see here that this is the continents colored by depth. I think this is the parts of the model where there's more than 5% contamination by the continents. And there's a lot more on the African side, where the continents are in pink at the surface, than on the Pacific side, as expected. I'll just show you a movie of this, or two movies. We're looking on the African hemisphere on the left-hand side and the Pacific hemisphere on the right-hand side. And you're going to see that snow that comes slowly into the model. It builds up over time. And there's going to be more on the left-hand side than on the right-hand side. And so this would be consistent with that, this could explain, if that geochemical signature is true, why there's a difference between the plumes that are from the African side as opposed to the Pacific side. And that could be continental contamination in the last 200 million years or so. All right, and this brings me to my conclusions. I think I've been pretty good for time. All of this to change a must to a may, okay? The history of volcanism is as compatible with moving blobs as it is with fixed blobs. So in other words, the lowermost mantle is free and the blobs do not have to be fixed. The blobs may be moving, which is consistent with current understanding of global geodynamics. It's not to say that someone couldn't come up with a model in which the blobs do not move and actually make subduction zones move. It's harder to do because one has to have a fully dynamic model, which these weren't. These were models in which actually, so they're driven from the top. Okay, so there is an opportunity for someone to look at a bottom-up model. The blobs could come together and break apart similarly to continents at the surface. So maybe we have blobs and superblobs. And the African blob may have come together in the last 100 million years, as opposed to 200 million years proposed by other models, and 550 million years or more proposed by the people who established the relationship between the blobs and the volcanoes. And finally, it's possible that the African deep mantle domain was enriched by the subduction of continental material. Thank you for bearing with me, and I'll entertain any questions you might have.
So does anyone have any questions? And that goes for people on a Zoom as well. Yes.
So is there any structure to this process, or is it completely random?
So the question is there any structure to the process, or is it completely random? Can I clarify that by process, you mean the process that shapes the blobs?
Yes, yes.
Yeah, so the structure is very much the subduction history. And so what's happening in the models is very much, I'll do it in a 2D sense, this. Not exactly this. When the slabs sink, it's a push. And so there's essentially the velocity field is moving down away and forcing other material away from that. And the second part is if the slab is actually advected, it will also take the real estate down there. So there is a structure to the process in these models. It is that the slabs move the blobs about.
Yes, Andrea.
Your model points that would indicate why a subduction zone begins.
So the question for Zoom is, why do subduction zones begin? Yeah, so that's an excellent question. There's several models out there. A second, actually, there's another question that's interesting. Why would it terminate? Also, is a good one. Several models out there. There are several models out there for that. One of them is at a transform fault, one of them is at a ridge, and one of them is at an arc, a young arc. They all have drawbacks, and the last one is at a passive margin. If it's at a young arc, you need to have had a solution zone before, so it's chicken and egg. The passive margin one has not been shown to work very robustly, but some people are arguing for that to be occurring at the moment offshore Iberia. Another place would be offshore Argentina. And then in the Pacific, we've had in the Pacific Ocean, there's places where it seems that transform faults might be a good place for that to start. So the Tonga Kermadec one is one where people have spoken about how, why, when did it initiate? That's a more recent, at 50 million years ago. It's not solved. But these are the 4 possible scenarios I know of. And obviously in the models, in the tectonic reconstructions, they come in and they die. Mostly they die because the ocean closes. That's the simplest way to think about it. Or because a mid-ocean ridge intersects the trench. So that's the case along the West Americas, where in the south now you have the basin and range and you've lost. So the subduction zone has gone to transform fault there because there's no slab to subduct anymore. Or rather, sorry, a ridge subducted and the slab is sinking and the rest wasn't pulled down. Yep, right.
Yes, Alan?
There are a couple of questions. One is, like to hear your opinion about the age and birth of the Paleo-Pacific and the existence of the Pacific block.
Well, so for Zoom, what's the age and birth of the Paleo-Pacific and the longevity of the Pacific blob? And what you asked for is my opinion. In these models, if I look at my models, if I take them at face value, it's always there. However, a known limitation of these models is that they don't have subduction zones into the Pacific realm as much as they should have. I think to answer this fully, then you go into the idea of supercontinents closing by introversion or extroversion, which I would like to entertain about, and you're my captive audience just now. The idea being, if you think of the Atlantic Ocean, which is the last one that opened, which is the breakup, one of the main phenomena in the breakoff of Pangaea, you open that. Then from here, you've got 2 options. Actually, you have 3, but I'll concentrate on 2. One is for the Americas to go all the way and come to us, and that is called extroversion. Now, from a mantle convection point of view, that's difficult because they have to go over the Pacific blob that's pushing up. The other way to do this is to close the Atlantic Ocean again, and that's called introversion. Okay. And so some people have argued that Rodinia, which is the continent, supercontinent 1 billion years ago, was split up by extroversion. If that's the case, then the Pacific blob should be younger than the last slabs that went over it, maybe 200 million years younger. And that would make it maybe 400 million years old. If it's not the case, it might be 1 billion years old. So I don't know, Alan, in my models, it's 1 billion years old. It doesn't mean it's 1 billion years old by any stretch of the imagination.
One other probably more difficult question, which also shows my ignorance, and that is, we're obviously talking about the effect, lateral effect of subduction graveyards. Yep. On the edges of the blobs. But what does, shall we say, topography on the top of the floor have an effect throughout? Because obviously, the floor is a very dynamic thing. The relationship between the solid in core and the outer core is very dynamic and causes magnetic field to wander around. Okay. So what information is, or active information is there on so should we say the dynamics of the outer cores? Okay. So Alan's question for Zoom is, or second question,
is the models I've presented, and that's why I put this slide up, show that the slabs push the blobs. And Alan's question is, well, there's topography at the core mantle boundary, and that topography is very dynamic. And does it affect where the slabs go and where the blobs go, if I understood correctly? And I would actually flip that on its head, I think, because a lot of that topography arises from convection in the mantle. And so where slabs are pushing down, the core will be depressed, and where there's upwelling, the core. So that's the dynamic aspect of it. The second one is the ellipticity of the core, which I know some of my peers take as a constraint for tomographic models. So all in all, they're intertwined. And then the question I don't know is how much processes within the core influence that topography. It's an interesting question. My gut feeling is that it's driven from the top. That's what these models show. And then, but is it possible that the outer core shapes the topography of the core mantle boundary and dictates where the blobs go? Seems a stretch to me, but I don't know if it's not, I can't say it's impossible.
Yeah. So we had one question in that corner there.
Well, I was just going to ask whether or not with the integrity of the blob, that fusion dominate over advection.
Yeah. So Errol's question, and I think it's specifically for the blobs, is whether diffusion dominates over advection for blob mobility. So certainly in the slabs, both processes occur. This slab that sticks around for a very long time, once it's at the bottom, it's all a diffusive timescale, and that's why it's very slow. And that's why, and then it sticks around so long because it's been there for a very long time. I'm focusing on the slabs now, even though you asked about the blobs. And then for the wiggles or the slab tracks I'm showing here, this is all the advective process. The one that dominates, well, they both contribute. So the advective ones are the broom, if you will. But once you have a slab down there, you need to heat it up again. And that's going to be on a diffusive timescale, and that's going to be longer. I haven't thought about this as long for the blobs. Both would be occurring. You see plumes come up in the models. That's the advective part. And then you see they stick around down there, and that's the diffusive timescale. So they both at play there. So for the blobs, they're controlled internally. I think it's diffusive processes, and then they receive whatever in these models from the slabs. So the advection is from the slabs.
We have a question here.
Do you have any idea what the block would be in the blob versus not the blob? Like how different?
Yeah. So
I know on the images they're showing is like red versus blue. But,
yeah.
How different is that?
Yeah. So a question from Lloyd for Zoom is, what's the rock in the blobs? Do you have any idea? There's two main models out there, actually, and one that meets them both. I just want to go back to my initial conditions. Sorry, that's a lot. My initial condition is a homogeneous layer, and that's more consistent. So there's no reason why the layer would be homogeneous at a billion years ago. Okay, but that's what I assume. It's the simplest. When I do this, I assume the blob material was there, and that's slightly more consistent with the idea that it's a primordial material. If that's the case, it would be linked from the segregation of siderophile and iron and siderophiles from the rest of the mantle. And then you would have had, it's the freezing of a magma ocean, essentially. That's the idea. And it would be iron enriched, and there would be, and you could have melt actually at the bottom. You could have interesting, fancy physical chemical processes down there. That's one school of thought. And that fits quite well also with the slabs sweeping things away. The second school of thought is drastically different, and the blobs will be made from slab. So that's the one Gordon likes. And so the blobs would be a slab graveyard. So there's two ways to do this. Essentially, so with the sweeping, that doesn't work too well. However, some models have shown that if the slab pushes the blob might integrate some of the slab material. Okay, so in that case, you'd have the dense parts, so that eclogite and stuff like that, that would be down there. And then there's a hybrid model in which the base of the blob might be the dense iron remnant from a magma ocean, and the top of the blob might have some of these enrichment from slabs. So, and then the last thing is the density is debated. My preferred one was plus 1.3%. And then depending on the constraints people have looked at, tidal tomography gives 0.5%. And then there's a thing called Stoney mode tomography gives 0%. So, and then other models like the one I've used here, the ones I've used here have predicted several percent. So we don't know, it's probably small. There's lots to be done there, and I think that can be solved only with seismic tomography or seismologic methods.
Any other questions?
It's pizza.
Yeah, thank you everyone again for coming, and yeah, please enjoy the pizza and beer.
Thank you. Thanks for having me.
I'll send you